record. Then let's share the screen. And let's start. So, okay. GEng 200 January 25 2021. And what we are going to cover today we will talk generally about probability rules. And in particular, we'll talk about conditional probability, we'll talk about independence, we'll talk about, if time allows, total probability rules or total probability rule, and finally we'll do Bayes theory. And if we manage to finish all of those today, this will mark the end of this chapter, and we will be ready to move to the next chapter. We are a bit behind, but I'm trying to go slowly at the beginning of the course so that you warm up. The thing that I want to mention before we start, at the quiz, I graded the quiz over the weekend. Most of you did very well. I think you can easily distinguish between deterministic and random processes. Probably you need to practice more on how to come up with the sample space, how to write it down, the sample space. But other than that, I think most of you did well, and I hope you continue doing well. Your quizzes, as we mentioned, has 15% of the course grade. So keep the good work. Okay. So last time we finished with talking about axioms of probability. And these are the three main rules of probability. If you remember, the first one is the probability of the sample space is one. Let me put my phone on silent. And the second rule, so the probability of the sample space is 100%, is one, because for sure when we run a random experiment, one element of the sample space should occur. So we are sure that an element from the sample space will occur. If an element from outside the sample space happens, it means that your sample space is wrong. You did not count for all possible events. The second rule is the probability of any event is between 0 and 1. And this is, again, very important rule. You have to watch it in all of your answers, in quizzes, in exams, in homeworks. Don't give me a negative probability. Don't give me probability of 2 or 3 or 5. This means that you do not understand the axioms, which are the most important rules of probability. And the third rule is if E1 and E2 are disjoint or mutually exclusive, then probability of E1 intersects E2 is just the sum of the individual probabilities. And before we move on with today's lecture, probably one interesting thing to remember, since you are taking a probability class, what we call the Murphy's law. You heard this before. When someone faces a rare event, usually bad event, it says, okay, this is Murphy's law is in action. So Murphy's law says anything that can go wrong which means, in other words, if you want to reword Murphy's rule, so regardless of how low the probability of a certain event is, it will happen sometime and somewhere, maybe to you. So if a certain event is very, very, very rare, but it will happen sometime, somewhere. That are the rules of probability. All events will take place. Some are less common, more than more frequent, but it will happen sometime, somewhere. For example, what will be the odds or the probability that you buy a new car and just after you leave the dealer's showroom, you get a flat tire or you get an accident? This is a rare event, but it will happen to someone somewhere, in some countries, in some event, or maybe there are some events that are even more rare that will happen. Brahim, you raise your hand. Go ahead.
Doctor, can we say that Murphy's law applies on the first patient who got coronavirus?
Yeah, maybe the one that he was the agent between the animal and the human being. Yes.
Mm-hmm.
Yes.
Okay.
Good one.
Yes, very good example. Yes. So yeah, so that's what you probably heard it before in some movies or somewhere. It says Murphy's rule. Okay, or Murphy's law. Anyhow, so this was aside, and then let's move with what we want to talk about today, which is the first thing we want to talk about is simple. Based on the axioms, we'll talk about addition rules. And we talk about probability of union of events. And in general, we mentioned this probably before. Let me write it again. In general, probability of the union of two events is the probability of the first plus probability of the second minus the probability of the intersection. And as you recall, if A and B are mutually exclusive, which means A intersects B plus B, then we'll end up with the third axiom of probability. So this is straightforward. Let's see the case for three events. Three events case. what's the probability that A union B union C? In this case, excuse me, this will be probability of A plus probability of B plus probability of C. And then I subtract probability of A intersects B. I subtract probability of A intersects C. Sometimes your hand writes things that you plan to write in the future. Minus probability of B intersects C. And then I will re-add probability of A intersects B intersects C. And why is that? Let's see. We can easily prove this rule using the Venn diagram. So assume that this is event A, this is event B, and this is event C. So this is A, this is B, and this is C. And let's see, when we say A, the union of A and B and C, then we are talking about, I want all the outcomes that are in this area, right? This is the union. And I want to make sure that I count the elements only once. I don't want to count them 2 or 3 times. So as you can see here, we can divide this into many areas. So there are many areas. So I have areas that I want to make sure that I count them once. So let's see what we are doing. So I have probability of A. So with probability of A, let's put, I count this area once. Okay? And then I add probability of B. So probability of B will add all B. Then I will add this, and then I added this. This is B. And then plus probability of C. So I'm going term by term. Plus probability of C. So when I add probability of C, then I'm adding this, I'm adding this, I'm adding this, and I'm adding this. As you can see, we have some areas that are counted more than one time. So we need to take some action. We need to correct this by subtraction. So let me use the red for the subtraction. And then we subtract A intersects B. So where's A intersects B? So I subtract one of those and one of those. This is the area, right? This is the area. Then I subtract the area between A and C. So I cross one of the ones here and one of them here. Next, I subtract B intersects C. So I need to cross one of those. Oh, sorry, no. I need the area between B and C. So I cross one of those and one of those. So now, as you can see, all the areas are counted one time, except there's a missing area, which is this area, right? Because I crossed it. All of them are crossed by what I have been doing. And that's why I need to add this area again. So I add it back. And then we'll end up with counting all the elements, all the areas in
Doctor?
A and B and C only one time. Yes.
Doctor, I just
yes.
Could you please repeat why we need to subtract them? Yani, I didn't understand this concept. Yeah.
Your goal is to count the areas once. So if you, and we are talking about the general the general case where there's overlap between A and B and C. So if you say probability of A plus probability of B, when you say probability of A, then if we have some elements right here, right? So when you say probability of A, you count those elements under A. When you add probability of B, you add them again because you add all B. That's why you need to subtract A cross B once, because everything that's common between A and B, you counted it twice.
Okay, because all of them is union with each other, right?
Yeah, there is overlap between them. If for mutually exclusive events, like if we have something like this, I have A by itself, B by itself, C by itself, then in this case, خلاص, A union B union C is just probability of A plus probability of B plus probability of C. But once you start having overlap, you have to correct your formula, and that's why we have this general formula that will count. يعني خلاص, you don't need to account for everything. Just follow this formula; it will give you the right answer. Yes, go ahead. You have a question?
Yeah, Doctor. If we have two of them, for can you go down a little bit, please? Yeah, if we have, like, for example, B and C are intersect, and we want to find the union, we will subtract the intersection, right? From the
again, you can use this general formula for all cases. If, for example, only B and C are intersecting, then some of the terms will be zero. Probability of A intersects B will be zero. So you're subtracting zero. So it will not affect you. So this general formula is applicable for all scenarios. Okay, whether you have,
thank you, Doctor.
you have overlap or not. Okay. Fine. Let's do an example. An example that will live with us, and this kind of examples we'll see them very often in the next the remaining of this chapter and probably next chapter. Let's talk about the distribution of employed, unemployed, people in a small town. And let me, because there's a divider here, I will move down. I will plot it here because I need 4. Okay, so let me. I will need probably wider one. So I have here so in this town I have men, I have women, and then some of them are employed, some of them unemployed. Thank you. Lucky to have a generous neighbor at my office, always bringing me coffee to stay alert while teaching you. So I just got my coffee. Okay, so let's assume in this city or this town we have 460 men who are employed. We have 40 men who are unemployed, so total is 500. And then we have 140 women that are employed and 260 women that are unemployed. We have a total of 400 women. And then if we add, so this is the total here, this is the total here, this is 360 The total is 900. So what's the cardinality of the sample space? What's the size of this town? How many people I have in this town? 900, right? Okay. Now, if I tell you, if you go to this town without looking at the people, you just picked one person from the street randomly. What's the chances that this person is a man? So what's the probability of men?
5 out of 9.
0 point. Okay.
Yeah, so we have a total of 500 people, 500 men,
Yeah,
and the total is 900, so it's 5 over 9, right?
0.555.
Yeah, so 5 over 9. Let's keep it since it's not a an absolute number, so let's keep it as a ratio. What's the probability of women?
4 over 9.
4 over 9. Okay. So now I can ask, what's the probability of, if you pick a person, it will be an employed person. You pick someone randomly, regardless of that person, a man or a woman.
6
What's the
over 9.
probability that
6 over 9.
that person is employed?
So,
Yeah, we know.
2 over 3. No, not 2.
Yes, we
Yeah,
have.
2 over 3.
We know that we have 600 employed people in the city out of 900. Then this is 6 over 9 or 2 over 3. We know that 2/3 of the city are employed. Then this is the chances. Like if you pick someone randomly and you ask him or her, "Are you employed?" If you do this more often, 2/3 of your trials will be employed people. Then I can ask, what's the probability of man and employed? The probability that when you pick someone randomly, it will be a man
10 over
23 over
27.
45.
who is employed. Fine. Let's agree on something, Shabab. Let's agree that intuition and يعني السبيد and الفهلوة is good. You usually you get the right answer, but in probability I advise you just to follow the rules. And when things get complicated, what you might feel it's right may not be right. So let's follow the rule. So and means intersection, right? So probability of men intersects employed. And according to our rule, so this equals probability of men plus probability of employed minus probability of, oh sorry, and oh sorry, yes, you're right. I messed up, it seems. Yeah, this is, I don't need to do the rule here. What's the probability of men and employed? From the table right away, you can get it,
Doctor,
right?
We
multiply.
can, Doctor, by the way, make circles in the table.
So this is the men, and this is the employed. So what's the intersection?
460.
So it's 460, 900. Okay. Right. If I ask what's the probability of man or employed, and you care, you went to this city, you need help. So you need a man, can help you a man, or a person who's employed, regardless, a man or a woman. So this is what I was talking about. So men or employed. So this is probability of men plus probability of employed minus probability of the intersection between men and employed. So probability of men, we have it, 5 over 9, plus Probability of employed is what? 2/3. And then you subtract the probability of the intersection, which is 46/90. And here, where you need to check that you get a number between 0 and 1. If you do any miscalculations, you may end up with negative number. You may end up with number that's greater than 1. So make sure that you do the calculations right.
Victor,
Yes.
can you repeat the middle step, the payment plus employed?
This one?
No, the last example, but the middle step.
Okay.
The second.
So again, the rule is, let's assume being a man is event A, being employed event B. So what's probability of A union B? A union B is probability of A plus probability of B minus probability of A intersects B. What's the probability of A? What's the probability of men? We have it. 5/9. What's the probability of employed? Probability of employed, we have it, 2/3. And then we need to subtract, according to the rule that we just learned, we need to subtract probability of A intersects B. So what's the probability of the intersection? Probability of the intersection, we found it to be 460/900. So 460/900.
Clear, thank you.
According to the rule that we did. Okay. So this is straightforward. Let's move to a little bit more interesting topic, which is conditional probability. Let me put a red line, since this is an important topic on what we are going to study. So where do we use conditional probability? Let's say in some occasions, we have a certain prediction or probability of an event However, another event happens or takes place that changes our expectation of the original event. So in this case, we deal with conditional probability. For example, assume that you are whatever, you are in a competition and like 10 students applied for the competition. All of them are good. Let's say three male students and 7 female students. Okay. So since all students are good, I can come to you and ask, what's your chance that you will win? You said 1/10, because we are all good. We all did well. It's up now with the panel. That's the referees who will look into what we did, and then they have to decide. So from your point of view, your chance to win is 1/10. So now I come to you and I tell you this. I tell you, okay, I talked to a guy in the panel and he told me the winner is a man or a boy, is a male student. So in your case, you have some extra information. So now your chances increase as a boy or as a male, right? Because you know there are only three of you. So your expectation, your probability for the future changed because of another event. I told you a male is going to win. So this is a related event that happens which changed your expectation or your prediction for the future. So now we need to learn how to cater for this using equations. So the way we write this is probability of A given B. So the way we read this, probability of event A given that event B has happened already. So you want to write this in red. So event A did not happen. We are calculating its probability. Event B already happened. And we want to see its effect on probability of A. And the rule for that is probability of A given B is very simply probability of A intersects B over probability of B, and of course, given that probability of B is a positive number that is non-zero. So this is the important rule for conditional probability. Right. Let's see how do we apply this rule. Let's follow up on the same example. Okay. So what we said is we mentioned what's the probability of employed person. So if I tell you go and pick someone randomly from the city, what's the probability that that person is employed is 2/3, right? From the table. Right. So now, what if I ask you what's the probability of an employed person given that that person is a man? So in your way to pick the person, I tell you, I was with you and I'm telling you, okay, we are picking this man. And now we will ask him whether he's employed or not. So before we ask him, since we decided on that it's a man, now things have changed. Why? Because we know that in this city, more men are employed than women. So now, if we want to apply the rule, what will be this probability? We follow the conditional probability rule, which is the probability of the intersection, the probability of employed intersect man over the probability of being a man. So what's the probability of employed and man for 60 over 900? What's the probability of being a man? 500 over and you can close this. So this will be 46 over 50, which is 0.92.
Doctor?
Yes?
So in this question, we picked a person and we want to ask him whether he is a man or whether he is an employee or not.
Well, this time we need to ask whether he's a man. But yes,
Sorry for that.
but yes, the idea is to pick someone randomly. So you go, and the way to do this correctly, you have to close your eyes and then pick someone randomly without targeting a man or a woman, and right away talk to the person. Are you employed? And you hear the answer.
Yeah, I know, no, but my question is, like, we already know, like, did that already happen? Like, we already know that he's a man, and we want to know whether he's an
Yes.
employee or not, right?
Yes. No, so the
okay.
second one, so
Thank you.
the difference between those two, yes, it's like you are opening your eyes before asking the question, and the second one, خلاص, like you are blind, just pick someone. It's like you have a drone or a robot who does not differentiate between men and women, and just asking who's employed, who's not. So as you can see, the probability has increased. So 0.92 is larger than 2/3. So what you can say is that picking a person randomly from the town this experiment results in 2/3 probability prediction. Picking a person randomly from the town, and sorry, a person randomly from the one, and finding if that person is employed has 2/3 probability. However, getting an extra information that the person is a man increases the chances of being employed to 0.92. So it's conditional probability. It's like you can think of it as if you are resizing your sample space. So now, if you get an extra information that he's a man, so from the table, your sample space is no longer the 900, it's rather the 500. And then you know that 460 out of the 500 are employed, and then this will be your new probability. Okay, let's do another quick example. Another example. In throwing a dice, we know that S, the sample space, is 1, 2, 3, 4, 5, and 6. And let's define some events. Let's say event A, we have an even number when we throw the dice. So A is 2, 4, and 6, which means what's the probability of A? We know that the dice, we have
1/2
equally probable events. So it's 3/6, which is 1/2. Let's define another event B, which is the number is less than 6. I'm getting a number less than 6. So B is 1, 2, 3, 4, 5, which means probability of B is what?
5/6.
5/6, right? So now I can ask you, what's the probability of A given B? So what does that mean? It means I'm conditioning A over B. So what does it mean? How does this experiment is taking place? So imagine that you are sitting in a room, and the room next to you, somebody throwing the dice. So I'm asking you, what's the probability that the number is an even number? You tell me it's 1/2. Then I ask, what's the probability that the number is less than 6? You tell me 5/6. Okay. So someone went to the other room and he asked the guy, and the guy told him the number is less than 6. So we know that he did not tell him what exactly the number was, but he told him that the number is less than 6. So then I come back to you and I ask you, what is the probability that we will have an even number, given that I know that the number is less than 6? So 6 is no longer possible, right?
So 1/2.
No.
Doctor, could you repeat the last part, the question part?
Okay. So I'm just trying to, for you to visualize what do you mean in this specific example of conditioning A over B. So keep in mind again, yourself, you are interested in getting an even number. You want to calculate what's the probability that you are getting an even number, right? So someone throw the dice in the room next to you. You don't know what's the outcome, but I went to the other room and I asked the guy, what's the result? He did not tell me exactly what I got is less than 6. Okay, so now I come back and I ask you, you originally told me that the chances that we will have an even number is 1/2. Now I'm giving you extra information to condition on. I'm telling you that the number we are getting is less than 6. What's the probability that we will get an even number, given that the number is less than 6? So what's your new sample space? What are the options that of the experiment, given that it's less than 6? So what are the numbers that are possible? It can be
2 and 4. Yes.
2 and 4 that you are interested in, 2 and 4. But what are the possibilities? Possibilities are 1, 2, 3, 4, 5, right?
Yes.
Because we know that 6 is not possible anymore. So we have 5 possibilities, and you are interested in 2 and 4. So we expect the probability to be what? To be 2/5. And this is what? Let me, I see some couple of raised hands. So let me just complete it and then I will take your questions. So probability of A given B is probability of A intersects B over probability of B. So what's the probability of A? What's the intersection between A and B? Intersection of A and B, it's probability of 2 and 4 over probability of B. We know probability of B is 5/6. What's the probability of having 2 and 4 in the general experiment? 2/6, right? It's 2 out of 6 over 5/6, which is 2/5 as expected. So go ahead. Who raised his hand? We have 2 raised hands. Problem is that it goes. So please, whoever raised your hand,
Doctor?
Yes.
My question is, I think you already answered it, but I just want to make sure. We are assuming that number 6 will not be a possible outcome, right?
Yes.
So
we
remove the.
Yeah, the guy told me the number is less than 6.
Okay.
So if you want, if you want to solve it by intuition. But as I said, always better use the rule. The rule says
No, because I get confused. Like if I thought B probability of A over B means I want B and A to be right in the final outcome. But I
Yes.
didn't know that number 6 is already excluded. You will never get this number.
Yes, this is not read as probability of A over B. This is probability of A conditioned on B. Probability of A conditioned on B. And then it's always probability of A intersects B over probability of the conditioned on event, which is probability of B. So again, it's like you are resizing your sample space so that you calculate your probability in a more meaningful way. Okay. So probably I will pause and take the absence, and then we can continue. Let me go to. You may want to go to log into your Blackboard so that you can check in. So I'll go to attendance, and you have 3 minutes. Please, I don't want anyone at the end or now tell me I could not check in. There is no codes. You just need to check in. So checking in have started. You have 3 minutes. We'll pause for 3 minutes for you to check in into Blackboard. Inshallah, people are started leaving after taking the attendance. I have to warn you, once last semester, I took the attendance twice at the same time, the same day. So I can't do that. So 1.5 minutes. I will resume the lecture in 30 seconds, but the counter will have 1 more minute for those who still are trying to log in. Okay, fine. Let's. So you have, for those who did not check in, you have still 1 minute. Please check in if you didn't. Let's have some notes on conditional probability. So again, if A and B are mutually exclusive, then probability of A conditioned on B equals 0. Why? Because by definition, probability of equals probability of A intersects B over probability of B. And for mutually exclusive, what's this for mutually exclusive? Or disjoint events, we know that probability of A union B equals 0. So mutually exclusive events, there is no point of conditioning A on B. So this is the first note. The second note is conditional probability. We should always remember conditional probability is a probability. Is a probability, which means should be between 0 and 1. So again, if you get a negative number or if you get a number that's greater than 1, then there are some problems with your calculation, which is very common with conditional probabilities. If you are not using the rule correctly, then you will end up with some wrong numbers. Finally, what's the probability of the sample space conditioned on any event? B. Any guesses? One, I see someone who wrote one, right?
Okay.
Yeah, I saw someone who wrote one. Why? Let's see. And again, sometimes if your intuition did not help you, just apply the rule. So by the rule, probability of S conditioned intersects with B over probability of B, right? So the intersection sample space has everything. What's the intersection of the sample space with B? We know that this is B over probability of B, which is 1. So conditioning the sample space on any other event does not because sample space is bigger than any other event. So this, by the way, this rule may apply to any other event A that's a superset of B. So if B is contained in A and then you conditioned in B, then probability of A is 1. So if I tell you if B was, let me write it down. So even if B is part of A, then probability of A given B is 1. It's like B is, when you throw a dice, B is number 2, event B is event number having number 2, and then A is an even number. So if I ask, what's the probability that you get an even number given that event B happened, which is 2? So for sure, this will be 1 because 2 has happened and 2 is an even number. Okay. Let's move to the second topic that we want to talk about today, which is related to conditional probability, which is independence. And again, let me put a red line under independence because it's an important topic, and let's define it. So we say two events are independent if any of the following conditions is satisfied or true. If one of the following condition, only one is enough to make two events independent. So what's the first condition? First condition is when we condition A on B, this does not add or change anything in our belief about A. So this means knowing that B happened does not affect our belief about probability of A, B of A. So this is like, if we go back to the same example that I started with, if you are applying to a competition, you have 3 guys and 7 girls, and you are all good. So if I ask you what do you expect? What's your chances to win? You said 1/10. So if I told you that I hear from the panel that the winner is a female, then that will affect your. You'll be happy. So because your chance now is 1/3. But if I tell you I was talking to the panel, and they told me that the winner is really smart person, even though I know some of you might think you are smarter than others, but no. So this is an independent event. So nobody is smarter than the other. Then you said this did not add to you. Still, it's 1/10. Or I told you that one of the panel told me that he's hungry. So this is a totally different event or information that will not add to you. So that event and what you are talking about is totally independent events. So this is the first condition. The second condition is the same. So probability of B given A equals probability of B. So this is equivalent condition. Third condition, probability of A intersects B, which is probably the most used condition, probability of A times probability of B. So if the probability of the intersection is just the product of probability of A times probability of B, then this is the condition for independence. Okay. Right. Let's do some examples and see. Let's do some examples. Again, let's do in throwing dice. Let's define some events. Let's say event A, again, it's 2, 4, 6, which again means probability of A is 1/2. We know this by heart now. And let's say event B is 1, 2, 3, 4, which means probability of B is what? 4/6, which is 2/3. Right. If I ask what's the probability of A intersects B, what's common between A and B?
2 and 4.
2 and 4, right? So what's the probability when you throw a dice, you have 2 or 4?
1/3.
2/6,
Two
which
over
is
six.
1/3. Right. So now let's see. What's the probability of A given B? So let's apply the rule. Probability of A given B is probability of A intersects B over probability of B, which is, what's the probability of the intersection? It's 1/3. What's the probability of B? 2/3. So this is what? 1/2, which is the same as probability of A. Which means, what does this mean? It means knowing that B happens or happened did not give any extra info that affected the chances of A. So if let's go back that in the next room, somebody is throwing the dice and you are interested in having an even number, right? You are interested in having an even number. Anas, give me 1 second. Getting an even number. So I went to the room and I asked the guy what happens. He did not tell me what number he got. He just told me that the number he got is less than 5. So it can be 1 or 2 or 3 or 4. So your expectation that you are interested in getting an even number. What are the chances to get an even number? Your original chances were 1/2. So now your new chances is also 1/2 because it's 2 or 4 out of 1, 2, 3, 4, which is 1/2. So your guess will not be better than before, right? The chance that you are looking for is the same as before. Anas, go ahead.
Yes, doctor. I would say for the event that we have so far, a probability of A over B, here they are independent, right?
For this specific example, yes. Here, event A and event B are independent.
What if we have B over A, doctor? The opposite, the reverse of probability of A over B.
Let's see. Let's check. So probability of B given A equals, again, probability of B intersects A over probability of A, which is, again, 1/3. What's the probability of B? What's probability of A, sorry? 1/2. So it's 2/3. So which is probability of B. So why is that? Because we know, as I said, any condition of those these are equivalent conditions. So if A given B told me that A and B are independent, so for sure probability of B given A will equal probability of B, because if A is independent of B, then for sure B is independent of A. Okay? And if you want to check the third rule, it will just confirm what we know already, because probability of A intersects B, we know that this is 1/3. Probability of A, we know it's 1/2. Probability of B, we know it's 2/3. So when you multiply those, it's 1/3. So you just need, so notes here, you just need to check one condition of the 3. You don't need to check them all. Second thing to note is independence do not or does not imply that there is no physical relation between events. Like in this case, we are talking about 2 events, about numbers resulting from throwing a dice. Yani, because the first example, as I mentioned, the referee is hungry and the other event is the results of the competition. So In that case, there is no relation, physical relation. But this case, yes, there is a relation. You may want to check yourself. Check if the previous example, when B was 1, 2, 3, 4, 5, in this case, A and B will not be independent. In this case, A and B are dependent. Okay? Type. Also note, another note, that if A is independent of B, then A is also independent of the complement of B. So if A has nothing to do with B, then it also has nothing to do with the complement of B. How can we show this? We know that we can write probability of A as two parts, probability of A that intersects with B prime plus probability of A that intersects with B. We know this because A can be looked at as two parts, one that intersects with B and one that intersects with B prime. Then take A intersects B prime to this side, then it will be probability of A minus probability of A intersects B, and then this is probability of A minus, we know A and B are independent, then I can write the intersection as the product, and then I can take probability of A outside, which leaves probability of B, and then we know that 1 minus probability of B is just the probability of B prime, which means we just proved that probability of the intersection of A and B prime is just the probability of A times probability of B prime. So this means that A and B prime are also independent. And you can check in the above example, what's B prime in this example? B prime is 5 and 6. Check also, I will not do it. Check previous example. B prime is 5 and 6, and then try to find whether A and B prime are independent or not independent.
Teacher, about independence, can you draw it on show independence on a group of circles to know what it is exactly? I know the rules, but I don't know what exactly it means to be independent.
We cannot show it through a Venn diagram because it has to do with the values of the probabilities. And I cannot plot. Yani for this plot, if I plot something like this is A and this is B, and each of them will have outcomes, right? So those two events can be independent or not independent based on the values of those. For some values, they will be independent. For some other values, they will not be independent. So we cannot visualize it. Okay?
Yeah.
Okay. Right. Few other notes in the remaining few minutes that we have. Note also, another note. If probability of A is greater than 0 and probability of B is greater than 0, then A and B can't be mutually exclusive and independent at the same time. So if two events are mutually exclusive, they cannot be independent. Again, remember, probability of A intersects B equals 0 or mutually exclusive, while probability of A intersects B equals probability of A times probability of B for independent. And we assume that both are non-zero. So both have values. So they cannot be mutually exclusive and independent in the same time. Actually, if they are mutually exclusive, it means that they are not independent. Why? Mutually exclusive, it means that they do not have any outcomes in common. Like if you are throwing a dice, A is even number, B is an odd number, right? So if I told you B happened means an odd number is a result of the dice. So in your mind, you will think that, okay, this information means that A will not happen because A means an even number. So being mutually exclusive, it will give you some idea about that there are some relation between the two events. Let me put a final note and then I will take any question. So a final note for three events, A, B, C, we say they are independent if all the below conditions apply. So if we have three events, it's not enough to check one condition. B intersects C equals probability of A times probability of B times probability of C. I need to check also all other I need to check that each two are independent. Of B times probability of C. So we need to check all conditions to prove independence. Okay, so probably I will leave you with an example. Solve on your own. On this specific example, so assume I have a sample space from 1 to 8. Probability of each is 1 over 8. And then assume event A is just 1, 2, 3, 4. Event B is 1, 5, 6, 7. And C is 1, 2, 3, 8. And check if A, B, C are independent. And you will find that they are not. But check it and confirm it. You will see that first condition will apply, but you start doing the second, third, and fourth, you will have the conditions will not be satisfied. Okay, I think I need to stop at this point. We are running out of time, and I have. If you do not have a question, feel free to leave. I saw a raised hand, so I'll be around if you want to ask questions. So please go ahead, Rahman, I guess. Who raised the hand?
Doctor, no, it was mine. I have a question. I got confused about the dependent and the independent. So can you like tell me verbally an example where we have like intersection and both possibilities are independent?
Here, the example that we solved, here A and B, if you plot A and B here, they have in common 2 and 4 in this example, and they are independent.
You mean by independent that the percentage of the possibility will not change no matter how many intersection we have, right?
Yes, it depends on the values of the elements in the intersection. They might be events to be independent, they have to have intersection. If they do not have intersection, as we said, they cannot be independent. So to start with, to be independent, they have to have intersection, and then based on the values of the elements, they can or cannot be independent. Okay?
Okay, Doctor. Thank you.
Sure. Any other question? So I will stop sharing and I will stop recording.